My name is Jeff Garland, and what I'm going to talk about today is SIMD libraries in C++. And actually, one thing I need to do real quick here, plug in the laptop so we don't run out of power halfway through. Hold on a second. For those of you who do not know me, I'm one of the 3 people who's been to every one of the BoostCons, CppNow conferences. So I've been programming in C++ for, since the 90s, unfortunately. Tells you how old I am. But been very interested in libraries from the very beginning. So because libraries bring access to functionality. So SIMD is also something, that's been around for a very long time. And it's nothing really new in a lot of ways. In fact, the first vectorization instructions go all the way back to the 1950s, which you might be surprised to learn. But for a long time, SIMD capabilities and the capabilities in Cray computers and so forth were the supercomputing of the day. And of course, in high performance applications today, they will use a combination of both SIMD instructions and as well as threading and other distribution mechanisms when they're working with really, really large models. But that sort of embarrassingly, parallelizable construct is a little bit less interesting to me because I don't happen to work in high energy physics or some domain which actually requires that. So what I'm interested in is, can I start to apply SIMD functionality in libraries and algorithms in ways that bring benefit in terms of performance? So I'm definitely not the world expert on SIMD. If you came here thinking that, well, I'm sorry. But on the other side of that coin, this stuff is actually going to be coming to you very soon in a C++ standard, very likely. So I have another role in my life, which is I work on the standardization committee. And for that, it's really, really important for the standards committee to get input from the community. I don't know if you all know this, but basically the standard is driven by the community. So everything I can do to increase that community, make it bigger, get more eyes on this library before it's in C++ 26, which is where it's targeted, that's an important thing. So that's why I was saying earlier in Library in a Week, there's a tie-in here. I'd like people who are interested in this subject to work on SIMD algorithms, SIMD functions, and try it out, see how this library works. And I'll explain a little bit more about what I'm talking about in a second. So one of the motivations as a programmer, right, is to actually use the machine that you're given in a full way. And of course, as C++ programmers, we think, this is a bare to the metal language and we can use the entire machine. I can tell you that you're barely touching the machine if you're just writing standard straight line C++. And Sean Parent made this point in a keynote in 2000 something. Neither he and I can remember. The video doesn't appear to be online, but he's remade that point at C++ North last year, and he goes into more detail about this, but it's probably less than 10% of the silicon if you're just using a straight line program that you're actually using in a modern CPU, and of course in a GPU, you're probably using 0. So there's a lot of wasted material there. And if this can help speed things up, then maybe you're going to want to use it. Okay, so, but to really use it, right, we have to be able to get beyond the basics of, some high performance physics application. Okay, so here's the outline of the talk. I'm going to give a little bit of intro. I'm going to motivate why, programmer intervention is going to be required to actually use this. I'm going to talk about various SIMD libraries, and I split those into 2 different functional groups. One is a high-level application library that just, you use it, and it does SIMD under the hood, and you don't care. So that's a very high-level thing. There's a lot of these in C++. And then I'm going to talk about development libraries, which I think is where the primary focus of the talk comes. And then the last half of the talk is really about what is proposed for standard SIMD. How would you get access to it? It's in the parallelism TS since 2018, so it's been there for a while. I can tell you that the ergonomics of trying to use it are not easy. And this is one of the problems we have in C++ with libraries like this. The standardization documents are not reference guides. And so even people in Library in a Week that want to work on this, you could buff up the CPP reference pages with examples, and that would be a tremendous advantage for the community in terms of understanding how to use it. I know when I first looked at this 2 years ago, I kind of dismissed the TS because, frankly, I couldn't get it to work really fast, whereas other libraries I'm going to talk about today, I got to work right away. And it was pretty obvious, that they worked out really well. So, all right. So, oops, sorry, wrong direction. All right, so what is SIMD? Single instruction, multiple data, otherwise known as vector processing. Math applications have been the obvious domain forever, but there's a lot more to it now. As I said, the first instruction sets for vectors were in 1966. The modern processors, as we know them, really started to appear in the late 90s. AMD had a thing called 3D Now. If you're old enough to remember that, well, I'm sorry. And Intel followed with SSE instructions. And there's been a continuous evolution in processor silicon devoted now to this. And of course, the applications have exploded as well as we get into neural networks and things like that. There's a lot of applications in those areas. So overall, this intro is going to give you a little bit of a taste. This is a huge rabbit hole. I can tell you that you can spend many, many hours of your life understanding how to write algorithms and program in SIMD. Okay, so what's a sort of simple, very straightforward kind of thing that you can do with SIMD? Well, you have a vector. It is, a collection of 4 things. In this case, I've shown, a register, if you will, that has 4 things. And so one thing you can do is you can basically have an operation against that vector and produce another vector. So that's, multiplying 0, 1, 2, 3. I've shown this as integers. Of course, floating point and other kinds of types can be here. And basically you get the result out over here. So that's one of the kind of basic things you can do. And I keep going the wrong direction. Another kind of thing you can do is you can actually just do operations vector to vector, produce another vector. So in this case, we're adding essentially these 2 vectors. So this is why things like vector processing and a lot of the physics kinds of things which are heavily matrix math sorts of things fit very well into this paradigm. That's why this paradigm has been used. And by the way, no criticism of the ASCII art. It's highly sophisticated. But anyway, so another kind of thing that you can do on a vector in SIMD, and again, I'm keeping this really, really straightforward stuff because there's a lot more things, but you can take a single vector and you can reduce it down to a single value. So in this case, we're going to do plus across this vector. And so 3, 2, 1, that's 6, 0 is 6. So you can reduce back down to a single value. And of course, you should already be thinking that sounds a lot like an algorithm, that we already do in lots of different ways. So why do we care? Well, you're writing code in C++, otherwise you wouldn't be at this conference more than likely. So you probably have something, you probably care about performance somehow. So in certain easy cases, you can make the argument that, you can get a sort of like 4 to 16 times speed up. But we don't probably want to do that if we have to write compiler intrinsics and read compiler intrinsics and understand that. So there's another problem with a lot of the SIMD stuff, and that's portability. So this is where, the C++ library can help you because it can ensure that there will be portable solutions that you can utilize across different kinds of silicon and different compilers and environments. Okay, so 4 to 16 times. How do people feel about that order of magnitude of performance increase? I got 1 thumbs up over here. Yeah, a couple. Yeah. How many times have you worked on optimization where you were able to get that kind of performance upgrade easily? Yeah, it doesn't come easy. And I'm not going to say it's going to come easy here either, okay? Because it's going to require you to think differently and so forth. So I think Fedor is here somewhere in the areas. So one of the things I was going to mention is one of the things that happens when you start writing SIMD code is that it becomes branchless. And he's got a great talk from, was it last year at CppCon on branchless? Yeah, so if you're interested in branch prediction and modern processors and how they work or don't work as the case may be, his talk was about, getting branchless computing. Well, it turns out you're gonna kind of start thinking that way and you're gonna start working that way when you start working with SIMD algorithms. So I think that's another sort of side benefit that, you get out of actually working on this. So what are some of the basic ways we can get access to SIMD? So the simplest possible thing is, we can depend on the compiler to do the work for us. Wouldn't it be great if the compiler would just do the work for us? Well, we'll see, but don't get your hopes up too deeply because just unrolling a loop is only a very small part of a program and it's not so easy. C++ is particularly bad at this, as it turns out, for reasons we'll discuss. As I mentioned, I don't want to write compiler intrinsics. I have no interest. I programmed in assembly when I was early in my career. I'm not interested in going there again. Thank you very much. Pragma flags. This is another way you can get access to the loop unrolling part of it in particular. So OpenMP and the various compilers, they implement various Pragma flags. So you can put those and tell the compiler, please, 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 unroll this loop for me. Does everybody know what I'm talking about when I say unroll a loop? Yeah, okay. You got a simple for loop, you're iterating over a collection, and it will bring them into a vector, do the processing that you're doing, and I'm going to show you an example of it in a minute. So high-level interfaces that are portable, that's what we want. All right, so can the compiler just do it? So I've written some code here. And this is the part of the presentation where the fun begins at CppNow because people start looking at your code. And I assure you, all of this code has been compiled and it does work and it does what it does. And there are Godbolt links and so forth through the presentation so that you can go play with this stuff. So what have I got here? I've got a function that is going to basically add 8 things together. It's a pretty stupid function. I don't think I would ever write this professionally or even, for fun. But I wrote it in particular because, this is basically C, right? Like, shouldn't, the compiler be able to optimize sort of the simplest thing? We don't have any fancy C++ here. I mean, the only fancy C++ here is this one, which has an std in front of it. You can't see because I, took it off for slide production. Anybody know, by the way, that works in C++23? Yeah, that's a range. That's a range being printed by standard print. That's awesome. Okay. Thank you, Barry. Thank Barry Revson when you see him for doing the hard lifting. By the way, that was, interestingly enough, being able to do that was the first library in a week we attempted. And with IO streams, we didn't make it. So anyway, but there it is. So that's the only C++ in this program. So the question is, what happens to the compilation here? What does the compiler produce? Well, when you start looking at the main, the assembly for the main, sorry, did I say I was going to show you assembly? I'm sorry. Any assembly aficionados in here? Okay, so it looks promising, I got to say, because all this vmove stuff here, is vectorized operations. But there's one little problem, and that's that the function that we actually are attempting to vectorize doesn't vectorize. It simply does the standard thing, which is, it looks through, it does a comparison. Am I done? Jumps back. It goes through the loop one by one. So why didn't this vectorize? Any ideas? I'll do Steven down here.
Aliasing.
Aliasing, exactly. So the compiler's first job is to produce correct code. And it can't tell that output pointer that you pass there is in fact, not in the same range as the inputs that you just gave it. So if it vectorizes it, it's just not going to work, potentially. So it won't vectorize this automatically. All right, let's write something that looks a little more like C++ because we are a C++ conference. So I still don't really like this function because of the returned array parameter here, the first parameter. But, at least I'm using an array. I know the sizes of it. And, the code is a little better. Probably in the loop, I should have used the size. That would make the thing a little more generic, right? So any thoughts on whether the compiler can vectorize that one? Well, no, it can't. I won't show you the assembly, but it can't vectorize that one. Now here's where it gets interesting. It turns out that if I write the best version of this function, I would claim it's the better version. Again, the array loop should, the for loop there, should be testing the size of the array instead of doing it the way I did it here. But basically, I declare a return value, I fill in the return value, and guess what happens? Very nicely, the compiler actually vectorizes this, believe it or not. This return value is, guaranteed to cost nothing. There's no copy here, right, because of C++ 17 language rules. So you actually get that as your output, and it actually works pretty well. So the compiler can actually vectorize things. This is an argument for writing pretty code, I guess, or writing nice code. So it actually did that without any help. But I'm still going to argue that to really exploit SIMD processing, you really have to just think differently, because data structures and algorithms that are just unrolling a for loop is very limited in its capability. So as I mentioned, standard SIMD is proposed for C++ 26. I also pulled this quote from a talk from an HPC conference in 2016. And basically, this is a former Intel employee who worked on the compiler team, worked in the intrinsics area, working on all of that. And basically his point was that in HPC applications especially, the compiler just not going to do it for you either, even though those are sort of the embarrassingly vectorizable things. You're going to have to actually intervene and do things to actually make use of the instruction set well. Okay. Okay, so SIMD and C++. So typical applications, and I'm going to show you a few of these high-level libraries before we dive into, how we can do things in a better way. So Math on vectors and arrays, that's the obvious one we've talked about. But there's a lot of other things that are maybe not so surprising either. CRC calculations, something that has to traverse a large data set, do some kind of computation on that data set, and hashing, interestingly enough. Google wrote something called highway hash, I don't know, 5, 6, 7 years ago now. And you can go find that on the web, where they vectorize the hash function and they vectorize the way that the table works and so forth. So that apparently has a very good benefit. And sort. I mean, it doesn't get more basic than sort right now. It's probably going to be only on fundamental types like, doubles and floats and so forth. But, having a vectorized sort is certainly a benefit. So some of those libraries, here's a list of some of these libraries. I'm not going to dwell on the details of how they work or so forth, but what you will see commonly is that all of those things require the programmer to actually change, your standard bubble sort or whatever sort you're basing it on. You do it in a different way. I should also mention Bob Stiegel's talk. He's not in the room. From a few years back, called Adventures in SIMD Thinking. And he goes into this, for a very long extended period of time, motivates a sorting algorithm, uses SIMD intrinsics to do it, which is great, except for that I don't want to do SIMD intrinsics. I want to write high level C++. So at the top of the slide is, to me, the one that is the most interesting library here. Anybody not heard of SIMD JSON by now? Okay, well, a few people. Well, go get it. Okay, so SIMD JSON is claimed to be, and there are performance numbers, a 15 times speed up over rapid JSON, which is supposedly the fastest hand-coded, very performance optimized thing. So that 15, 16 times speed up, that's what we were talking about before. So their tagline is gigabytes of JSON per second. And if you have a chance, Daniel Lemaire, who's from Canada, has done this work, and with, I think, some friends of his, but he's the primary behind this. And this library, I can tell you professionally that, we use this library on very large JSON data sets. And it is fast. It is very fast. And it also has a nice interface. And you don't have to know. That's the whole thing, right? Like, you don't actually have to know that it's SIMD underneath. It just mostly works. There's one little part of the interface where you have to get things into what are called a padded string. That padding is there so the alignment and so forth can work, but it's pretty seamless. You can just construct one from a regular string. So that library is also very interesting because of the data structure that's underneath it. And Lemaire goes into this in one of his talks quite greatly. It's called a tape, is what he calls it. And this is the thing that allows the SIMD instruction set to find all the delimiters in the JSON and very rapidly, for example, tell you the result of whether or not, this is actually valid JSON, for example, right? So, if you think about your standard JSON, you're going to have curly braces and other delimiters of very specific nature. And it turns out a SIMD algorithm can basically tear through that at a very, very quick rate. There's a lot to it. Okay, it didn't just come out of the box. We had to look at it a lot. Okay, so what are some of the other things that are going on in the ecosphere from the standard library point of view with respect to SIMD? So we do already have parallel algorithms. Who has used the current parallel algorithms? We got a couple hands, 3 hands maybe. Yeah, which is about my assessment of it as well. The implementations are tricky to get, and they generally require additional libraries. outside of what is in the standard set, especially if you're working with GCC. I think Microsoft might be better about this. Seems like there's not a lot of love there. So one of the interesting topics of discussion before this stuff gets standardized needs to be the follow-on of, are we going to now put a SIMD type of option on these parallel algorithms? Or should we just be doing something completely different? So that's an open discussion, and it's a design point that needs to be examined, in my opinion. MD, yes?
Could you comment? I thought they added the unsequenced specifically so you are allowed to use SIMD. It doesn't actually do anything currently, but I thought it permits you to do it.
I think unsequenced allows you to do any kind of unsequenced, so it could be threaded, it could be, it doesn't say.
Well, parallel allows threaded. Just parallel by itself allows threaded, but unsequenced allows SIMD.
Okay, so they're saying unsequenced. Because I thought I read, and maybe I got this wrong, but I thought that there was going to be a new addition to that set of delimiters specifically for SIMD in one of the follow-on papers. But maybe it's already there, and I mistook it. So
I think you're both right.
Okay.
ANSEC is for SIMD, but there's a proposal for even more, but I'm not sure.
Okay. Yeah. So yeah, there's an explicit extra proposal now for the parallel algorithms associated with the SIMD stuff, and then I don't know why. If it was originally unsec was for SIMD, I don't know why. And Olivier's not in the room, so we don't have our resource to tell us exactly why that came about. Okay, so another data type that's been recently introduced in the standard, again, this is C++23, is MD span. That's a multi-dimensional span. So that's taking something that can take a contiguous sequence and create it into a multi-dimensional data structure for access. So this particular type is very specifically crafted to allow parallelism to exist underneath it, and to allow implementations and optimizations to use GPUs, use SIMD capabilities. There are follow-ons to this as well for linear algebra and so forth that may very well also get into C++26. We'll see how that goes. But if you're working in this space and you're working on multi-dimensional data, that might be an interesting thing to look at, because certainly that's part of the question is, how to actually arrange particular data. But MD span, just like span, it's a view. So it is a way to look into a contiguous data set, as I said. So literally a contiguous data set. Okay, so I don't want to dwell anymore at the application level. I've scratched the surface here. You can go on a deep dive and find lots of other things in lots of different other domains, C++ libraries that are doing novel things, especially in graphics processing and so forth with SIMD. Okay, so the next section is to talk a little bit about some other developer libraries. So these libraries in particular are targeted at, writing C++ and being able to vectorize C++, but not having to write intrinsics, basically. Okay, and so we basically have, I've picked 3 libraries here. There are more, but I picked these 3 because when I started doing research on this a couple of years ago, these are the ones that kind of came to the top. And so XSIMD is a library written by one of the high-speed trading groups. And so that's obviously getting utilized in high-speed trading. So it is C++11 as its base. And it has a thing called a batch type. And so the batch type is really the vectorizable type. And we'll see a little bit more. I'm going to show you a couple examples. So the expressive vector engine, that's Joel Falcou, who's been to this conference many times. He's got some presentations of Eve online, I think from a couple of years ago, CppCon. And they use the terminology wide type for the equivalent of the vector. So I'm going to show you examples from both of those and just show you, kind of what the surface area of it looks like, how these libraries at a very skimmish level look like. And then I'm going to do a little deeper dive actually into Agner Fogg's library. This library is actually the simplest library of all of them. There are 0 templates in this library, which is a stunning thing for a C++ library. By the way, who has been to Agner's website?
It's beautiful.
Yes, it is. Yes, it is. So Agner deserves a lot of credit for explaining to all the rest of us how modern processors work and how things laid out and things you should know about the hardware underneath. So if you're interested in performance, you definitely want to go see his site. But there are no templates, and it's a series of types. So it's very much like the C type approach to an API, but they are actual classes. But we'll see a little bit more about that in a minute. Okay, so here's what XSIMD looks like. So basically, this is right out of their page. I didn't invent this one. So basically, this is, I want to take a mean. And as you can see, this batch type here is specified using a double, which they use an initializer list to initialize. And then they have this mean function, which is a template here, and basically says, yeah, whatever fundamental type it is, whether that, batch type is integers or whatever, I just want you to add these two things together and divide by 2, and that gives you the mean. Yes, David?
How big is the batch? Are you just supposed to know that AVX is 4 things? Or?
That's correct. That's an excellent question, which is how big is the batch? And that little other annotation there that says XSAVX is a constraint on how large that can be. Now, I think they also have just fixed type sizes, which is kind of what a lot of you might be expecting to see here. But I think really what this is able to do is it is able to use the best possible size, given the AVX instruction set. Okay, so this is where it gets non-portable, right? Because as soon as you say, this is an AVX instruction set, then that means you better have an AVX instruction set or it's not going to work. I don't know if these can sort of downgrade, right? Because for 4 elements, you obviously don't need a real AVX instruction set. But my suspicion is that you might run into problems because they're doing some code generation underneath the hood of that template. Good question. And keep on that question because that's going to keep coming up. There's more to it than that. Yeah, back here.
Just to clarify, the mean variable there is also a batch, right, of size 4 in this example. Or is it?
It's a batch of T, the type double, and this architecture thing, which is some kind of an enumeration that they're using to specialize the template under the hood. So yeah. So it's not bad. It's an interesting approach. There's not too much stuff here that you have to do, but there are some issues, perhaps. Yeah.
So other than initialization, which is an improvement, what does it do that I can't do by simply writing under M26D in GCC, which has overload for plus and divide?
There's a lot of algorithms and other things that actually go along with this. Right, there's a whole library here. JF has got an answer in the back.
Troll you, but do you want to talk about ABI at this point?
Which
ABI.
What about it?
Well, you're passing it as a function parameter.
That's right. Yes.
And the architecture can change.
That's correct.
One processor can support multiple architectures.
Right.
That's a big consideration in the SIMD, the std.simd proposal design is API stability where you want it, where you don't want it. And if you just use the intrinsics, you don't get that.
That's correct. And well, so the intrinsics.
You roll your own.
So JF is basically, just to summarize for the audience, he's saying that, one of the big things about standard SIMD is trying to have ABI compatibility. We'll talk a little bit about how that happens or doesn't happen, as the case may be. But the point here is one of the downsides of this library is it basically is locking you into a certain kind of instruction, and that function, that mean function there, is actually parameterized by that. So you're not going to be able to call that. You're going to have to generate a new mean function for every instruction set, potentially. And so you'd like to avoid doing that, obviously, if you've got a large scale set of algorithms, because so makes the weight of the library. But back to Fedor's question, well, the only thing it gives you is that, you have a nicer syntax. And of course, in a simple slide program, okay. But, in a big program, it gets much worse, yes.
I just want to say that this being a nicer syntax than using the intrinsics is arguable.
Okay, all right.
So potentially you could use like a using declaration to move AVX to be not copied twice, but just one place in the code. And then you can change it and compile and move from AVX to AVX2 to.
Yeah.
Now you can do the same by saying using my word equals under M256D, and then you will switch to M512D in one change.
So the discussion here is that maybe for this very simple, trivial case, the intrinsics are just as good. The intrinsic portability, by the way, if I didn't say this already, it's actually surprisingly good, right? Because it turns out that most of the vendors have basically adopted the same set of intrinsics that Intel produced. And so that it's actually not unportable. But having said that, then there are some that are specific. So if you're down the intrinsics rabbit hole, you may or may not have portability. Standard SIMD is going to stick to things that are going to be mostly portable across lots of different architectures. All right, we got another Timur.
Question, since people mentioned intrinsics, like even if they're portable to some degree, it's only going to be Intel anyway, right? So if I have like a Mac with an ARM processor, it's going to be completely different.
No, it turns out they implement. So GCC's implementation basically depends on the fact that the intrinsics are actually portable to Mac and so forth.
Oh.
Yeah.
Okay.
So that surprised me too. I thought they were Intel only, but that's not the case.
I did not know that. That is interesting.
Yeah. All right. Well, one person learned one thing in this session. It's been a success. Okay. All right. So let's move on and take a look at Eve. And you may recall that, one of the things about Eve is it targets a C++20 base. So it's trying to use advanced C++ in terms of things like ranges and views and so forth. So it's at a different level. And again, I just pulled one of the examples from the documentation here to give you a flavor of what it's like. There's a lot more library that I'm not showing you, but just to give you an example. And that issue we just talked about has disappeared from this slide, right? Suddenly we have this wide thing and it's a float, and we didn't specify what instruction set it was. That was basically determined by how you compiled your code and the sizes of things that you created. And I'm not certain it may actually do adaptations for when the size of your data is too big, to fit into a vectorized instructions. Don't quote me on that. But
so what's it for? Is it a size or the value?
Oh, the 4 is a value. So it's going to initial, or no, maybe that is a size. It's probably the size, yeah. Okay.
Well, if you go by container rules, if it's in curly braces, it's the value.
Well, Yeah, so maybe that was not a good idea. What's interesting about that too is in a lot of these libraries, you can initialize the vector by doing exactly that, right? Like if you want it to all be 4, you would initialize it. But so I'd have to get back to you and look and see whether that's actually the value or the size. So I wouldn't put it past Joel though that that's not the size, that is the value, and that
And it replicates. So
it just replicates it, and it's figuring out, okay, how wide can I make this thing on this architecture? So it'll use the largest register it can, and it'll make it 4. Timur.
What's up with the second auto there? Is that a typo?
No. So that second constructor is really interesting, isn't it?
Just the parameter is a lambda. The second parameter of the lambda.
So that's a novel and interesting idea, right? Basically, we have a generator function here that is basically going to iterate across every one of the elements in this wide type and apply this function over here. So this is why I think actually the 4 actually is an initialization, because if you look at that, he's basically going to return 1.5 f times I plus 1.
Yeah, but what's the second
What's
auto?
the second auto? Yeah.
I don't know. Okay. For some reason, they have a parameter that they pass into their generation function, a second parameter.
It would be natural to
And-
give you the last value, the last generated value, to have a generator.
Yeah.
running on the last.
I don't know. All I can say is std.simd has a very similar idea, okay, but it doesn't have that second parameter. So I don't know. I didn't dig deep enough on this particular function of Eve to find out. Okay, so what else is here that's interesting? So another initialization down here. You see that we're basically getting, a C array, and we're basically giving it the reference to the C array, and it's able to just construct it from that without any extra annotations about, what SIMD is or isn't, and so forth. And anyway, this is doing some polar function, checking. The application isn't really important. The whole point was just give you guys a little bit of a flavor of what these libraries look like. Yeah, I'm back.
Looks like we're given not the CRA, but just a pointer. So it's unclear what happens with the size.
Yeah, so the comment is that on this last line, it's a little unclear what happens on the size. And yeah, but presumably he's able to figure out what the size of that is, since it's compiled right there. But yeah.
Well, there's literally no way for Y2 to know the size, unless it assumes unless it's fixed in the definition of the type.
It probably is fixed in the definition of the type on just a simple area big enough.
There's like 16 values, maybe.
It looks dangerous to me.
512.
It's not really code I want to write. All right.
32 bit.
Well, 512 is the
That's why I thought
is the largest.
Well, it's an array, not the size of a content.
Except that when but it takes not pointer.
All right, so let's move on to Agner, Fogg's vector class library, and just get a little bit of a flavor of it. As I mentioned, it's really a series of vector classes. I didn't sit down and count how many, but it's a whole lot. It has some other unique features like half precision floating point support. It also has some things like decimal to ASCII conversions written in SIMD. So it has some interesting algorithms in it that are sort of extensions on this library. And so, when you look at the documentation, you'll see a huge table like this that says, here's the bit size of the thing. Here's the number of elements per vector. Here's the instruction set it's going to map to. So it's pretty darn clear what is going to happen here. And indeed, it is totally clear what is going to happen right when I write this code now, which is the same code from the very beginning. Okay. And again, now you'll notice I've taken his vector class here, his 8i vector class, and I can just assign the values in an initializer list. I can call this add. You note I've gone back to the reference way of doing it here for the C. And you'll also note there's no for loop, right? Because we don't need a for loop now because we have vectors. And we're just able to add those two things together. So we have operators, right? We have the ability to say, vector plus vector is another vector. And what is the result? Anybody think this is going to vectorize? It's a vector library. It darn well better vectorize. So yes, indeed, this vectorizes almost exactly the way you would think it would.
There is no check for alias.
What's that?
There is no check for alias. If you happen to alias it, you get what you deserve.
You get what you deserve, yeah.
But that's fine because the way it's written, it does it in a single pass. It's only if it's...
But it still cannot.
Yeah, but aliasing isn't even a problem there because you write it after you finished with the reads.
I think technically the compiler could actually see that C is actually different than B and A. So, yes.
Only if it's aligned.
I think that because the add function doesn't have a for loop, it sort of like implies that there's no ordering, and the operator is allowed to add the elements whichever order they want. So aliasing is.
So what happens if you do pass the same vectors? And do you get UB or?
I don't know.
In this case,
We would
no.
have to try it, but I don't think so.
In
Unless
this
it's,
case, you're fine.
implemented in a strange way, it should be fine because it creates a temporary as a result of A plus B. Now there's nothing aliasing and it assigns it to C.
That's right.
In this case, you're fine.
Because it's single like.
It's going to do the addition.
And the loop is just fully parallel.
Yeah, I think what we would find if we went in here is that it's going to do the addition. There will be a temporary register which will become C in effect, and that's what will happen. So I guess that was one of the other interesting points of that 2016 talk. One of the other little tidbits I learned is that the machine has a lot of registers that you don't know about. It has the ability to sort of generate virtual registers as it needs to on the fly. And so that's one of the things that, if you're looking at assembly code, you're going to see, certain names for certain registers, but the reality is they can be completely different under the hood. And that's actually done at runtime. It's not done at compile time, ultimately. So the ability to map those registers around allows the machine to actually perform these capabilities rather well. Now, you will note, I had to write a for loop for the print because, unfortunately, this is not a vector. It doesn't have an iterator. It doesn't have a begin end. So it's not a range. So you can't just use the range print. So there's one other little thing. You might remember I had rewritten this function, to just do a return, which was really kind of nice. And then something really interesting happens when you do that with this library. It gets even smaller. So actually, the compiler is somehow able to throw away a couple of instructions that it was otherwise doing if I was passing by reference. So it looks like we should write good functions.
Which compiler is that? That's GCC, right?
This is GCC 13, yeah.
Oh,
Mhm.
okay.
Yeah. Okay, so question.
Yeah, sorry, quick question. You mentioned that the vector class doesn't support the iterator interface, and so you can't do like the print with the std ranges. If the vector class, is there a reason why the vector class couldn't just implement that iterator interface? Or is that just something we just didn't do?
Right, so the question is, could an iterator interface be implemented? And the answer is yes. It just, is very painful to write standard iterators. Anybody here write standard iterators? A couple hands go up. Yeah, how painful is it?
It's painful, but less painful than Zach's library.
Okay, so the comment is it's painful, but it's less painful if you use Zach's library, which is what's the name?
STL iterator.
STL iterator, which is in part of Boost. So his library takes a lot of the boilerplate out of it, basically. So unfortunately, at the standard level, the ranges and views and all that stuff has an immense amount of boilerplate required. Actually, though, Zach's library, as a side note, has been proposed to LEWG. I haven't talked to Zach about how the reception was. I'm not sure, but
It's so.
so were
leaning
you
positive.
in the? Yeah. Okay. All right. Well, that would be nice because once you've got ranges, having those iterators is actually quite valuable. All right. Do we have any more questions so far on where we're at? Okay. So the next part of the talk, the rest of the talk is about the proposal. This, as I mentioned, is going to totally skim the surface of this proposal. I lost count of how many pages it is. It's 100 pages or something. The merge proposal is just a large proposal by itself. And on top of that, there's unfinished business. So I'm going to show you some of the ugly warts that are there now. So if you actually try to go use some of this in its current form, you might be unhappy at certain times. Okay. So the primary naming here in terms of a concept is what is called a data parallel type. So the vectors that we've been talking about, the wide, these things, the batch type, these are called data parallel types in the standard proposal. And basically, you get a couple of different flavors of this. 3 primary flavors of it. You'll get SIMDT, a fixed size SIMDT, where you actually can fix the size just like you can in Agner's library. And then there's an element type, T, which is the arithmetic type, which is going to be chars, unsigned chars, integers, floats, doubles, those kinds of things. They're basically the integral types. And basically, the number of elements, is constant for each parallel type. That the number of elements in the type is called the width, right? Which is exactly what you expect. So these things have an ability to tell you what their width is, in part because we're going to have that secondary flavor. If we just use the SIMDT flavor, you're not going to know what the size of it is until the compilation happens. So that's part of, we'll talk about that in a minute a little bit more. But that's part of the ABI thing that JF was talking about earlier, where you'd like to be able to write this portable code. You don't know exactly which instruction sets you're going to compile for necessarily. Like if you're providing a library to somebody, right, in their compilation, they might not have the same number of registers as you have. So you want to be able to compile that internal code in a way that's consistent with what architecture they have. So we'll talk about these in some more detail in a minute. This last piece of it is something I haven't really delved into a lot, but if you've written SIMD code, one of the things you know is there's a lot of this idea of a mask. And when you're loading and storing and when you're calculating, a lot of times you want to say ignore certain values. So like in Eve, for example, there's this idea of being able to ignore the first value or the nth value in this particular array when you do this calculation, right? So if you want to say plus, on 2 vectors, but I want you to ignore the third one and the fifth one, right? For some reason for your application. Okay, so the SIMD mask is just a specialization of this same type, but for bool, and that has a lot of interesting properties. Okay, so we were talking around this earlier. So one of the things, if you read the TS today, if you went and dug into the several hundred pages of the TS, or you go to CPP reference, you'll see that, the bottom line is in the standards proposal, the change from the TS will be that the native ABI is going to be the preferred way. So that's why when you say SIMDT, you're going to use the best available. And again, that's going to depend on what you tell your compiler to do, right? What kind of instruction sets you allow your compiler to do. So there's this sort of weird thing where the implementation is effectively selecting that for you. That's going to be the default. The fixed ABI, which I'm going to show you examples of, in that fixed ABI, you get to decide the size. So that's sort of the standard thing that Agner's library and some of these others are doing as well. All right. So why don't we just add two vectors together? Only problem, right from the get-go, you're a little depressed because that nice constructor that you had in the other libraries does not work because there's no initializer list constructors. So your simple slideware doesn't work the way you want it to. But it's a surface area problem. It's a friction. It's actually acknowledged. Okay, so in the work that's going on now, there's acknowledged work to better integrate some of these things. I'll show you what all the rest of the constructors are in a minute, but that doesn't work, so it's a little saddening. But the other part works just fine. Oh, and so I should have mentioned here that the details are on this slide. You can go to Godbolt right now and, punch this in and, you'll see that, you're able to get this. So in this case, I've done the fixed size SIMD. So I've got my, int 8. I probably should have called it int 8 here. And I've just got my simple function that, basically does the add. So what do I actually do? Well, so this is kind of the code I have to write, unfortunately. So this isn't technically a constructor, but it's a factory function, if you will, that allows you to copy data. So basically, I'm giving no, did I? Oh my, I think I mixed and matched. All right, where's the bug, Stephen?
A is not a data, it's a C array. A data doesn't have a dot begin.
That's correct.
Yeah.
Yeah, sorry. I think when I did this initially, it was actually std array, and somehow I apparently swapped those out at the last minute.
You can fix it in the language.
Okay, that's language feature in a week. C arrays with dot begin. Hey, not a bad idea. All right, so this copy from does exactly what you'd expect it to do, and so okay, I have the same problem with the print down here. I can't use the ranges print because these things aren't ranges yet. Again, that's an acknowledged weakness in the current proposal. Keep in mind the TS was voted in 2018. Okay, we're in 2023. A lot has changed in those years, including the adoption of ranges in general. So that was still in work when this was done. It's understandable that the two things, don't line up completely now. Fedor.
Vector aligned. Aren't you being a little too brave on this?
Probably. That's another usability issue in my mind. Because actually, if you go read the paper, Matthias goes through this in some depth. That some of this is going to be changing. I should have also said, if you're going to write code with this, expect it to change because there are going to be a fair number of API changes before this is complete. Because
I would expect this to generate move DQA, and it should generate move DQU. Was there a default alignment on this?
Right. Well, we'll see in a minute. Back here.
So for the fixed size SIMD, what happens if the target architecture is too old and doesn't have those size vectors and only has like 4 integers that you can fit in a register? Will it fail to compile, or will it create an array of 2?
I believe it will fail to compile, but I have not tried it, so it's something. And again, part of the reason for giving this talk is to get more people like yourself actually trying these things and reporting potential usability. Is it what would we like it to do in that case? Probably we want it to fail to compile, or do we want it to somehow magically, use the biggest size it has and unroll things. Is that even possible? I think it is based on some of what other libraries do. I got a couple more questions. Timur.
So I have a question pretty much about this, like target platform. So for example, in audio and music software, like SIMD is used very heavily, but it's typically targeting consumer hardware. So whatever laptop or phone you have, you don't know upfront what instruction set is going to be available there. You just don't know. So you either compile for the oldest thing that you support, but then you don't get speed on the newer stuff, or you compile for the newest stuff. Then if you run that on an older laptop, it's literally going to crash because the instructions are not there.
Right.
So what people are doing is they're compiling their like signal processing kernel multiple times for multiple target architectures.
That's right.
Put all of that into the binary, and then you do dynamic dispatch. Like when you start your synthesizer or effect or whatever, you have like a little runtime check at the very beginning. What instructions are there? And it inherently is a runtime thing, right?
Yes.
It's not a compile time thing.
That's right.
Then you do dynamic dispatch. You say, okay, I'm going to use this like binary version of this, which is bundled into your executable, and then it kind of works. But this is, I think, what the whole industry is doing, and I wonder whether you will be able to do it with this standard SIMD or not.
Well, I think there's no. I'm not going to try to repeat the questions. I think we don't need to, fortunately.
You can make it as a language feature. So there's multi-versioning in like Clang and Linker and whatever. And so you can do that multi-versioning of your functions.
There is in GCC as well.
And in GCC.
And GCC.
We'll start doing that dynamic dispatch at the load time, and then always dispatch the right thing afterwards.
Right.
Okay, I'm going to ask you.
Like binary multi-versioning.
Okay.
So the whole discussion is about the fact that one of the things that you can do here with at least two of the modern compilers, I don't know about MSVC, I'm sure you can implement the dynamic dispatch on your own in MSVC, effectively, because you'll have different signatures for different sizes and so forth. And so effectively the idea is when you call a function, it's determined at runtime which one of the vectorized instruction overloads are actually called based on what the machine actually is. And by the way, like when you use SIMD JSON, you never tell it anything other than you've compiled to a certain level of instruction set, and it will dynamically actually fall back to lower levels. I think to the point where it will unvectorize completely. If need be. Yeah, over here.
You chose the fixed size SIMD here, which means that if you try to compile to an architecture that doesn't support it, it would crash. Sorry, it wouldn't compile. There's also just the std.simd version. Would that not pick the best for the architecture you're compiling for?
It should, yeah. Yeah, that's the general idea. Mm-hmm. Okay. Well, let's see, to Fedora's point, what we actually got. Oh, the only problem is I did not show you the main. I have the main in my other notes, so we can look at that afterwards to see what it actually did. I mean, it does work, but you'll also note there's more instructions here than in the Agner case, so it's a little less optimized. Maybe that's not a big deal. Maybe it is. Back here first.
So, if I understood you correctly, it's pretty guaranteed that the SIMD types fit in a register.
Yes.
So I think passing them by reference is sort of like a maximization in terms of performance. I think RDX and RSI here are addresses that get passed. If you would have passed the arguments by value.
Oh, that's an interesting point. I did not try passing them by value, but I don't think that's the pessimization that's happening here. I mean, you saw in the Agner Fog library passing them by const reference, and there was lights out, no issue.
I was just going to say, probably not a great idea to make performance claims without benchmarking.
Absolutely.
Number of instructions.
Yeah.
Okay, so that's a very good point that I overlooked saying earlier in the presentation. SIMD instructions have a cost, right? They cost more than your linear instructions to actually run. You have to load that data in from memory, which if it's, aligned in a straight line will happen very quickly. But there can be negatives. So there is no guarantee that this is necessarily faster. You're correct. And it could be the case that this 5 instruction thing is faster than the other one. My guess is that a performance expert that has written very clearly hand-rolled code, however, has actually picked the best possible instruction, which is why I brought that library up, because I think, if we're close to that, that's probably what it's going to be. But yes, we would have to benchmark, and I didn't have time to do that before this presentation. Yeah.
I just wanted to say that the extra instructions are not necessarily causing a performance penalty. Like the V0 upper is primarily to break dependencies, which helps performance because.
Okay. Well,
it's also part of the whole function call thing.
Right.
And the reason it wasn't there on the other one probably because it figured out it optimized the function itself.
Right.
Because the load here and the V0 up are entry and exit code.
Yeah.
Oh, another little detail I should have mentioned. All of this is compiled at 02. And it's compiled at 02 because a lot of this actually can't be, you can't actually compile it at 03 or you're going to just get the answer. You're just going to get the answer. It's all going to const expr away to the answer. And so as a result, this is even worse than David brought up. What's going on here? I make no claims about the perfection of it. I'm just showing you some differences. So, I was really more interested in will it vectorize and how will it vectorize in general. So that was what I was trying to get at. But yes, this is another thing. In the original TS, it was not const expr, but actually it got implemented that way as const expr. So as it turns out, this can actually work in const expr, which is cool, right? I can still write code with SIMD and it will work in a const expr context if that makes sense. So that again means applicability to your algorithms that you want to write. You don't have to be afraid that you won't be able to make it const expr. Okay, so for several other of these examples that I'm going to show, I just wrote a little wrapper here because writing that copy from thing all over the place is just ugly and whatever. So I just made my own little fixed vector here that takes care of the constructors. I think, things like span and array are going to get first class support by the time we're done. The paper hasn't been written yet, though. So, motivated people in our community need to make sure. I think Matthias is going to try and write it, but he's a very busy person, as you can imagine, just fielding, the issues with this proposal. Okay, we have an hour and a half, right? So we're 20 minutes? Okay. All right, so we should move along. So this is what the constructor set actually looks like. This first constructor is from a value. So that's where if you've got your fixed size or your other size, you will initiate the entire register with that value. That's the simplest one. We have a copy constructor. You'll notice the templatization against the ABI here. So that does appear in here, but they are actually defaulted. Contiguous iterator is another way. And again, to Fedor's point, the element aligned to is the theoretically safer version of that. So that's what's going to load in things, assuming that it's not aligned. And then I put copy from and copy to here. Copy to obviously is not a constructor per se. It's a function that is a member, and copy from is the similar, but the other direction, right? So one of the other things in the SIMD processing you end up having to do is you've got it in a SIMD register. Now you need to copy it out to some other thing somewhere else. So copy from is the analog to copy to. So remember that interesting generator constructor. I was actually on this slide and I just skipped over it quickly. That's the third one in the middle there. That's a generator function, and that's the same pattern that you saw. So in this particular example, I just, said, okay, here's a random distribution. By the way, this is another one that it would compile. It would just compile all the way down, I think even at 02, which is why I decided, okay, I'm just going to put a random generator here so you can't compile down. So I've just captured the generator here, and the int argument to the lambda there is basically the index into the SIMD vector itself. Okay, so you can go look at this. There's a lot more code around this, but that kind of gives you the idea of this, sort of generator interface. Yes.
Yeah. I'm thinking about the span constructor, and well, it's probably convenient, but standard span has no way to specify if the data is aligned or not. So you probably end up using unaligned load.
Right. So the comment is you probably, with a span constructor, will probably use unaligned. Yeah, my feelings on span are complicated because you're right, you don't know. And even worse, you would actually, I think, like to be able to use span the other direction, right? Like I'd like to be able to see the vector as a span and use it for parameter passing, maybe to ranges and so forth. But I think you can't do it because of data. Right, there's that little function on span called data, which basically gives you access to the data, and it's not going to work on a SIMD object. So, unfortunately, I don't know what we're going to do about that. Probably we're just not going to support span as an output, which again feels unfortunate. And maybe we should have not put the data capability on span, but then maybe span isn't useful without it. So maybe we need a span light. I don't know. This is why this stuff is hard, right? Like, you didn't think about the thing that was going to come along 2 or 3 years later where, oh, yeah, I'd like to treat that thing as a span. So I think what you're going to get is you're going to get a range. You're going to get a contiguous range with iterators, and that's probably what you're going to get. Yeah.
Actually, kind of related to the span line question. So you can put a line as on, or you could put it on span. You can put it on these. Now that takes care of the stack allocation. But now I go and say new one of these. Now I'm totally beholden to basically malloc.
The allocator,
But
yeah.
new does handle alignment.
You have overalignment, it's handled now.
Above the system alignment?
Yes. There's a special overload of new that passes the alignment of the object unit.
Yes,
And that will be called if it's
line
over
T.
alignment.
And it will over allocate basically.
Yes. Or it will do whatever it needs to guarantee the correct alignment.
But span has no way of knowing that the underlying storage is aligned, right?
Indeed, span.
There's a special qualifier supported in MSVC and GCC and LVM under align.
Yeah.
So you can use the qualifier to specify things are aligned. So maybe we should standardize that.
But does
Specify
that
alignment
dynamic
for
allocation?
everything in SIMD. It'll be great.
Does that
Okay.
take dynamic allocation?
It does whatever we want.
He's making up language features in the back.
It's already implemented. It's just not standardized.
Yeah.
Question.
Yes.
Are you talking about unaligned versus aligned, like loading of something to a SIMD register, or the actual SIMD instructions? Because they always have to be aligned, right?
It's the loading, and,
So the
and
loading,
it's the loading.
I've done
Yeah.
some benchmarking on this a bunch of years ago. Probably compilers have, like CPUs have completely changed, and I haven't done this again. But from what I saw, I think on older processors like Intel Core 2 Duo and stuff like this, there was a big penalty for like unaligned versus aligned loads into a SIMD register.
Yes.
But on all the new ones, the Intel ones, it basically doesn't matter. And
That's right.
That was several years ago, so I would expect that now it definitely doesn't matter anymore. On
That's
ARM,
right,
I
that-
think it's a different story, but like on the new Intel processors, they don't care.
It was even mentioned in the 2016 talk that the unaligned loads had been basically made fast now. So there's still going to be some problems, probably small thing, but it's practically unobservable. So I got 14 minutes left. I want to give you a few more notes before we go. So there's a lot of other pieces of this library than just the vectorized types. There's algorithms that do, things that you would expect to be able to do. So we'll talk about both of these just a little bit. So here's a simple program that basically uses the reduce, horizontal min, horizontal max. Those names are likely to change. That's one of the design questions and points. But basically, we're using copy from again, but the ABS here takes a vectorized type. So it's overloaded on the vectorized type. Reduce is also a standard function currently, C++17 algorithm. Hmin and hmax are not. The naming there, for reasons. But, so you can see that being able to do that thing I said in the beginning about, I've got a vector and now I can, apply a function and get a single value back out. Standard kind of thing that we want to be able to do. And so, yeah, those are going to be fast to doing that on a set of data. I also want to mention just a little bit about the operators. We saw in some of the other libraries, there's operators. There's a full complement of operators here on the SIMD types. So I'm using the fixed vec thing here to make the construction easier. I have another utility here that I'm not showing you, which is print stats, which is basically doing the function I just showed you with, min, max, and reduce, and taking a vector type in. And you'll note here, I get A and B, and then I have this line of code here. Auto C equals A equal B. So what is C here?
Fixed vector of bools.
It is a vector of bools. So basically comparing along the entire vector, the two things, and telling you, and then this all of function takes that vector of bools and says, hey, these should be the same because, by the way, B is a copy of A, right? I assigned it right there at that earlier line. All right, David's got a bad face on.
It's a SIMD mask. It's not.
It's a SIMD mask.
It's not the horrible vector of bool.
It's not vector of bool. Yeah, it's SIMD mask.
That's not why I'm shaking. We're fundamentally changing what double equals means in our object model for C++.
Mm-hmm.
There is a straightforward, if we wanted to make the meaning the same as everywhere else in C++, it would mean all of the A's are equal to all of the B's.
Right, it would include the function that's below, yes.
Right, so I think that while we need that function, we should not be spelling it double equals.
Mm-hmm. This is why I'm presenting this here, because I want people like you to think about this.
What's the size of C? Is it the same size as a fixed vector of int?
It is, yes. Okay. It's the same size. So the printout of what happens when you print this line is up here. It just gives you true, true, true back. Okay.
So sorry, I didn't mean. I meant the real size of the whole type.
Yeah, it's a fixed vector bool of 8.
One bit in an int.
Yeah.
Yeah.
It's really
Yeah.
either
It's the
zeros
same
or
design.
ones.
They always use one bit in whatever type you were operating on.
Okay.
Yeah, they're not smaller.
Okay, yeah.
Interesting. Yeah, David.
I assume that Agner Fogg's library didn't do the weird double equal thing. Why don't we just standardize that?
Actually, I think it might. I don't remember now. We'd have to go look at it. But yeah, this is one of the things is that when you look at the series of libraries here, right, like they all do things slightly different. I'm pretty sure Eve definitely does basically what the standard is proposed here. It will give you that vector mask or vector bools back. I mean, I agree with you. This is an interface design question, right? Should we spell it that way or should we spell it some other way? This is very succinct, but like you say, suddenly we've done the evil thing that you recommended against, don't operator overload in a way that isn't the same as everything else. And we're going to do it in the standard. Is that the right idea?
Well, as an example, what if you have a std vector of these fixed vectors, and now you do double equals on your std vector? Now, that doesn't work. It just breaks everything.
Yeah, but if the result is convertible to bool, it'll probably work.
But having a vector of things convertible to bool in general is probably a bad idea, which requires you to have a special case return type that just means the result of equality.
Mm. Yeah. Okay.
Names.
So there's a lot here. Like I said, this is a deep dive, or a shallow dive. So I'm going to apologize on this slide. I haven't got all the references here, but before I put them up, I'll get all the references to all the papers. There's like 5 papers in progress right now regarding this subject. So now is the time to register your objections to the form, the function, the capability. Use this stuff, play with it, see what you don't like about it, see what things you would like to have in it. Like I said, ranges and initializer lists and, first class support for regular integration with the rest of the more modern parts of the standard library like span and array. Those things are things that are projected to happen. We need to probably make sure they happen. Otherwise, as it is today, I would not want to use the library. And that is not a good thing for me to be saying. So I would vote against it coming out. Now, I think the way that they're going to try and do this is they're going to try and move the major thing and then they're going to patch it up before we're done. So that's...
Bad idea.
Yeah.
Okay.
What happens if they only get halfway?
Right. Fair enough. But maybe the committee and the way it works. So I got one in the back first here.
Does this mean that the std complex will be trivially constructible because of this? Because I need that. So this proposal is something that's in work. It's in LEWG for Library Evolution, and so it allows you to put complex values in and then treat them as vectorized, which is pretty common amongst the instruction sets. So I think I had you first.
Yeah, so kind of a big question sort of on all of this. So everything I see basically boils down to, well, with the exception of reduce, there was one slide on reduce, but everything else boils down to, we take the intrinsic types, and with a compiler intrinsics, I don't mean, the functions, I mean actually the types, under M256D.
Yeah.
We add the whole, initialize a list, whatever, iterator, that's the language scaffolding. But in terms of capabilities, it's plus, minus, equal, which is what I can already do. Anything interesting, kind of non-trivial, requires me to be able to do, at least shuffles or the masked adds or anything like that.
Some of that is in another paper, which I don't have the reference here, but there are other functions that I didn't show you today that are already part of the TS that do some of the functions you're talking about. But permutation stuff, like the advanced permutation stuff, you likely want to be able to do. You want to be able to say, go this way, go that way. That kind of stuff. That shuffle kind of stuff. Some of that is in a follow-on paper, so it's not in the TS. Tobias and then Timur.
So what happens if I have more data? Currently, we only talked about 8 or 16 bits of data. Usually, I have more of it.
Yeah.
Do I have to split it manually, or do the algorithms support me to split them?
It's a really good question, and to be honest with you, I should have played with it and I didn't. So we should play with it this week and find out the answer to it. But
because
I think
I would expect it to be done by the algorithm, because I don't want to divide my data by hand.
Right.
Because then I make all the errors.
I assume you can do arrays of this.
I don't know if the algorithm is written to automatically chunk. There is some reference to being able to do the chunking, I think, in a string example that's in the base paper, which again, unfortunately, is not on this particular page. Over here, Timur.
I just wanted to add to what somebody don't think I know your name, said about complex. This is actually a problem that like a lot of people I've heard are saying that I've heard somebody literally a couple of weeks ago, we discussed this at a C++ meetup, say that they will not use std.simd if that's not going to be fixed, which is that the complex isn't trivially constructible, and they have these huge arrays of complex numbers, and it's just too slow for them. And so basically they said, if std.simd is not going to fix this, we can't use it.
Okay.
And so I just wanted to say that it's a major concern, and I've heard a lot of people actually say this.
Good. So that's the kind of feedback I want to hear, because I want to, be able to represent that feedback. I think I have one over here first, and then Stephen.
Does this also include a basic math function? For example, the security is Intel has how the version is version that.
Yeah. So yes, there are capabilities to do the masking on at various points. So yes. Sorry, Stephen first.
I was going to say, I'm not sure how much changing complex would actually help, because for SIMD operations, you often want to split the imaginary and complex into two separate arrays rather than having a single array that has both parts. And a single complex type is incapable of representing that.
I don't know, Timur, did you hear that comment?
Sorry, no, I was distracted. Sorry, can you say that again?
Say it
I'm
again.
saying that for SIMD operations on complex numbers, for arrays, you usually want to split it into an array of imaginary and an array of real.
But you need both, like real, imaginary, real.
Right, but for
real,
SIMD
real.
operations, having them in that order is inconvenient.
I guess it depends on the use case.
Yeah.
I mean,
Yeah.
these people are doing some serious low latency stuff, and that's what they say they do. So I don't know what their use case is. I haven't looked at their code. They just gave me feedback. They were like, "Oh, you're from the committee. Can you please make sure they do this? Otherwise, it's not useful for us." I'm like, okay, I'm gonna mention it.
Is that you're from the committee is like I'm from the government, I'm here to help? Please, let's not make it like that. I think you're first.
I'm curious whether SIMD could work with strong types such as physical units, because it was mentioned that vectorized types are like instant floats and so on. But what if I have a vector of velocities and I want to apply vectorization to it? Is the only way to reinterpret cost or something?
Well, I mean, the author of Boost Units is sitting up here. I mean, I think at the end of the day, the units go out the window when you're actually doing the calculation, right? They are only a typing layer that sits on top. I don't know.
Well, maybe it could be made interoperable, but I doubt it would work without serious effort to make it work.
Yeah.
Because as far as I know, the SIMD doesn't allow user-defined types, probably.
No.
Yeah.
Yeah. Back here.
This is a comment on like all the libraries I've used for this, and that like they're really useful until a new intrinsic comes that's not supported, and you have to start bouncing in and out between the intrinsic use and the library use, and that sort of kills the advantage that you're trying to get anyway.
Interesting. Yeah, that's an interesting problem. Because, yeah, I think like unlike stuff like thread and so forth, there's like no native way to get to the underlying thing here. So, yeah, that might be a problem for some people. Yeah.
And have a related comment. Even if the intrinsic already exists, but only in single instruction set, like some weird shuffle optimized for something, then like what do you do on all the other instruction sets? Do you need to provide fallbacks?
Yeah.
If you include it in the standard.
And that's the general portability problem. And yeah, so there may be domains that this isn't going to cover. I skipped over it because I was out of time, but I do have actually another application that's completely not SIMD at all, and that is just give me a string of characters that represents an ISO standard date and validate that it's right. Write that code in SIMD. I've written that code, and it turns out that you can do that in a fairly short number of instructions. And more than that, absolutely certain that I can vectorize the construction of an actual like 64-bit integer value for a date and a time using some of the facilities here. So I haven't written that code yet. I eventually probably will. I might even plug it into boost datetime, who knows, for somebody to try out. All right, I think we're probably out of time, right? So, or yeah, okay. All right, well, thank you all very much. Appreciate it.